Hello and welcome to this tutorial titled Cartography and Making Maps. Maps are one of the oldest forms of human communication. Apparently, primitive people may have found maps to be useful as maps help mediate the physical world that they lived in with the inner cognitive world. These primitive maps have helped humans to transcend the limitations of individual ideas and beliefs of their surroundings into a visual representation of their physical environment. The result, a map, was a depiction of their surroundings which could be shared collectively. Maps have opened new possibilities for viewing the fabric of our planet. Maps facilitate decision-making, help us envision new scenarios, and help coordinate actions and new collaborative ideas. Now, it's very easy to create a map in ArcGIS Desktop, specifically ArcMap, but creating an effective map that tells a story and communicates ideas effectively, that can prove to be challenging. I explored the cave behind me earlier. I love these new LED flashlights, and I was fascinated with the pictographs I observed, which are ideograms that convey a meaning through a pictorial resemblance of a known physical object. These are drawn on a rock wall and are pretty well preserved, and they were probably drawn by ancient or prehistoric artists. Though it was a bit disturbing, at least in my opinion, to see this. These ancient artists created a map. And I'm only guessing here, though, it was probably a vision quest or something showing what was coming in the future. Airports, roads, gas stations, basketball players, or is that an iPad? Pretty good use of symbology anyways. Now during this tutorial, we will focus on two primary subjects, mainly cartography and making maps with ArcGIS Desktop. Cartography, the study and practice of making maps, relies on the notion of generalization and simplification. Generalization helps us reduce the complexity of the characteristics that will be mapped. As a map author, it's up to us to orchestrate the elements of the map, and it's up to us to choose those elements that will convey a message effectively to our audience. Modern cartography is closely integrated with geographic information science and is made up of many practical and theoretical foundations of geographic information systems. As the map maker, author, or cartographer, we are constantly making judgments about what to include on our map, what to leave out, and what to show in a slightly incorrect place. This gives us the power to lie with maps. Maps are an important part of our everyday lives. They provide a simplified depiction of the space that we live in and also highlight relationships between entities. In simple terms, a map can be thought of as a graphic representation of the physical features, both natural and artificial, using symbols or photographic imagery. Geographical phenomena, such as the town or city that we live in, are often so large or extensive that we must somehow reduce them to bring them into a manageable view. Maps help us accomplish this. We use maps in a variety of ways for transferring knowledge, for making decisions, and for recording data. Good maps are somewhat ubiquitous in that when we take a gander at their symbology and learn their story, their cartographic language communicates to us, echoing concepts in a variety of relationships and forms. In basic terms, maps reveal two fundamental elements: positions, also known as locations, and information about those positions, known as attributes. A treasure map revealing a pirate's treasure may look very different from a highly detailed contour map, but in fact, they have a lot in common. Both reveal information on location and attributes. These two elements, combined with other cartographic language, help reveal relationships. These elements which form our map can tell a poignant and powerful story. Though maps can also cause people to become very frustrated, as poorly designed maps are difficult to understand, inaccurate, and pretty lousy at communicating information. Unfortunately, a poorly designed map can often diminish the confidence of the map in the eyes of the map reader. One of the goals in developing a map should be to ensure that other individuals are able to review the map and understand its significance. That brings us to the study of cartography. Cartography is the study of making globes and maps. Cartography isn't something you learn in a short period of time. The subject of cartography is rather complex. Sure, some people think making a map is easy, but you know what? That isn't always the case. An effective map requires an effective design. Maps or rendering of certain geographic features have been a part of history for quite some time. Maps let us view the world in a scaled-down, abstract fashion. A new generation of map makers have embraced a new generation of technology. This new generation of technology is geographic information systems. Though I find myself pondering if life would be easier if we still drew maps on rocks, using dried raspberries as our ink. Well, at least the maps would smell better. Though maybe GIS is the better technology. Within a GIS, we can view spatially relevant data together in a composite view without having to smash raspberries. Though relying on the GIS to create a map for us automatically may not be the best option. Creating an effective and powerful map that tells a story requires attention to detail, understanding the map audience, and the overall purpose of the map. If a map is not designed properly, or if it tries to show too much information, the design may be a cartographic failure. Map design is rather complex. Would you consider a pretty map that is inaccurate to be a cartographic failure? I think I would. When I use a map, I try to learn from the map and extract information that can be usable for my particular needs. The quality of a map's design affects its reader's ability to extract this information. Making a map that is meaningful should be our ultimate goal. It takes time and effort to create a decent map. Taking time to design the concept of the map is typically where we begin. A well-understood concept of a map should help guide the overall design. Maps, as an abstract representation of the Earth, require symbols to perform the abstraction. Cartographic symbols or cartographic characters can be used to distinguish points, lines, and areas. These cartographic symbols have been designed by intelligent people to help us portray the real world using these entities or objects. Looking at a standard U.S. geological topographic map, 1 to 24,000 scale, the design of each symbol has been very carefully thought out to allow intuitive recognition of the main features on the map. The symbols on the map are almost like the words in a book. They describe information and tell an important story. The very nature of symbolization is generalization. So by using symbols, we end up meeting one of our goals of creating a map, namely generalization. We must remember that using symbols to generalize our map can have negative repercussions. Just by using graphic symbols, a map may appear to be inaccurate because of the method of symbolization and oversimplification. Let's look at a simple example. If we were asked to create a map revealing fishing access sites, our map design could employ symbols to designate the elements in the real world. In some parts of the world, a fish silhouette is a symbol often used to designate a fishing access site. This symbol, along with many other symbols used in cartography and on maps, do not necessarily have a universal meaning. So what I'm getting at is relatively few symbols used on a map have universal meaning, so keep that in mind as you're creating a map. Cartographers have long been concerned about how map readers perceive the symbols on the map. Is there an ideal size to use for the viewer to differentiate the symbols from other forms or shapes? In the case of the fish silhouette, used as a symbol to represent a fishing access site, where is the fishing access site? At the head or the tail of the symbol of the fish? Symbol design is one of the more important disciplines of map design. It's important to understand that both point and line symbols on a map often take up more space than the actual feature occupies on the Earth's surface. In this example, the cartographer chose to use an exaggerated symbol, which occupies far more space on the map than it does on the Earth's surface. By exaggerating the symbol, map readers can quickly determine the location of the fishing access sites. Using unique symbols on a map along with various kinds of marks such as dots, lines, and different shading patterns may require the map reader to constantly compare or go back and forth between the map elements and a map legend to determine what the symbology stands for. Virtually every symbol and every mark on a map will have some connotation. It will also result in some visual impact on the map. Symbol selection combined with symbol usage can strongly affect the communicability of a map. What makes a good map? Other than smashed raspberries, of course. What features do most people use on their maps? A map can be another sort of a traveler's tale, both an invitation and a key written in a universal language. I don't think there's a silver bullet to making a universally good map. The answer really depends on the need of the user. A soldier fighting in a war may have a different need than a long-haul trucker who is cruising down the highway. How about that canoeer navigating a watery maze trying to determine the location of the next big rapids? One of the initial steps is for us to determine who the audience will be for our map. In many cases, determining who our audience will be will help us refine our cartographic design. Will our audience be school children or professional adults? Close attention has to be paid to legibility of map features. It's always important to remember that the map may end up in the hands of someone other than who we thought our audience was going to be. No matter who's looking at our map, we want to make sure that it has a design characteristic that most anyone can follow. Each ingredient on our map should be evaluated to make sure it has the proper impact. What are the ingredients of a good map? What are the general components which make up a map? I'm not sure about you, but I sure am getting anxious to create some maps. But before we begin creating a map, let's discuss some of the important characteristics of a map. Our goal is to review some of the basic elements of cartography or cartographic design. Why? Well, our ultimate goal is to create a better map. By having this arsenal of knowledge of what makes a good map, hopefully we too can create a good map. First, we'll look at the basic characteristics of any map, such as the purpose, transformation, reduction or map scale, generalization, and symbology. Then we'll take a look at some of the components which make up a typical map, to include legends, north arrows, titles, annotation, and color. Speaking of color, I'm going to grab a handful of raspberries and eat them as we proceed through this next subject area. Raspberries contain a significant amount of polyphenol antioxidants, which apparently can provide protection against several human diseases. All right, this may seem obvious, but most maps have a purpose. They are designed by the cartographer to convey a message to the map reader. That purpose may be a road map showing the connectivity of roads and the underlying networks. It may be a pollution map showing the spatial distribution of sulfur dioxide being emitted from a coal-fired power plant. The purpose of the map often dictates the type of map. If the purpose of the map is to show topographic features, we create a topographic map. If the purpose of the map is to show population density, we could use a choropleth map, which shows the measurements of statistical variables. If the purpose of our map is to give general information about the precipitation of a region, we could create a climate map, employing different colors to show precipitation zones. Identify the purpose of the map you want to create. The examples offered are just meant to get you percolating and thinking about the purpose of your map. All maps involve some form of a transformation. When making a map of the Earth or some other planet, we transform a spherical surface, essentially the shape of the Earth, into an easier shape to work with. This could be a flat map or even a monitor on a computer. This transformation, also known as a map projection, is our attempt to portray the surface of the Earth or a portion of the Earth on a flat surface. This transformation process always results in distortion. So every map has some element of distortion, which may include distance, direction, scale, or conformality. Intelligent GIS practitioners will have defined the coordinate system and projection of their geographic information assets. They will also comprehend and understand which projections are best for preserving area, distance, and direction. Most maps are a reduction of the real thing, and as a result, the maps typically reveal information smaller than the region they portray. This proportion of dimension is also known as a map scale. When comparing two maps of a different scale, the maps are often considered a large-scale map or a small-scale map in relation to one another. The map scale is a ratio and represents a fraction. This fraction indicates how many units on the Earth's surface is equal to 1 unit on the map. If we were comparing two maps, one at 1 to 500 and the other 1 to 10,000, the large-scale map is the 1 to 500 and the small-scale map would be 1 to 10,000. Why? If we were to convert the ratio or fraction to a decimal value, 1 to 500 equates to 0.002 as a decimal value. A map scale of 1 to 10,000 converted to a decimal is 0.0001. Comparing these two values, 0.002 is larger than 0.0001. Our map scale, or relationship between certain distances on the map and the distance on the ground, are often revealed somewhere on the map. We can use a scale bar or a simple textual proportion, such as 1 to 24,000. Cartographic generalization is a key component to map production. In order to meet visualization requirements, real-world data are modified so the data can be represented on a map while still preserving meaningful and legible visualization. Because a scaled map represents a reduction of reality, in general, map features, often represented with a symbol, are generalized and made larger than the actual feature on the ground. Let's take a look at the scale and size of a map symbol used to represent an interstate highway on a USGS topographic map. This raster image does have an established coordinate system, so any measurement we perform in ArcMap should be true. The minimum lane width for an interstate is typically 3.6 meters. If we multiply that by 4 and then fudge in a little extra space for a shoulder width, we end up with about 25 meters. After zooming in pretty tight, we can see the symbol used to represent the interstate highway. Let's measure its width. After setting the distance units to meters, it appears as if the width is over 80 meters. In this example, designing a map for reduction resulted in an increase in line width. The USGS cartographers working on this map exaggerated the true width of the highway using the symbol so that the symbol would be visible at this scale. As a general rule, the smaller the scale of our map, the greater the need to generalize map features. Most maps use a graphic symbol to represent real-world features found on the ground. Therefore, maps are an abstraction of reality. Maps let us generalize this complex world that we live in. And as a cartographer, we get to pick and choose the symbols or features we want to represent or fit on the map. Most maps will have a legend or a key which will explain to the user the symbols that are used on the map. In our fishing access map, if we utilize a fish silhouette to represent the locations of each fishing access site, we would also include that same symbol in the legend and provide a description thereof. An arrow, typically pointing in some cardinal direction, allows the viewer of the map to determine the direction of the map as it relates to due north. Most maps use a north arrow. In general terms, it helps the map reader orientate themselves, and it indicates which direction is north. There are exceptions to this rule, as some arrows point to a different cardinal direction. A standard compass, a magnetic compass, is made up of a magnetized pointer, which is free to align itself with the invisible magnetic field of our planet Earth. True north is an imaginary straight line between you and the geographic North Pole. This straight line, often called the meridian of longitude, is a great circle that passes through you and both the North and South Poles. Magnetic north is the position of the compass needle as it points to the magnetic North Pole. In most cases, true north and magnetic north differ. Some maps, including the U.S. Geological Topographic maps, reveal this variation between true north and magnetic north. This variation is often revealed using degrees and minutes, either east or west. This angular difference is often called a variation. Magnetic declination, sometimes called magnetic variation, is the angle between magnetic north and true north. The declination is considered positive east of true north and negative when west. Computing the magnetic declination of the general vicinity of our map is pretty easy. Easy if we use the National Geophysical Data Center's website. From this webpage, I will enter a USA zip code and then click on Get Location. To determine declination outside of the United States, enter a latitude and longitude in these text entry boxes and then click Compute Declination. The computed declination is provided in degrees and minutes, along with an indication of how much it changes each year. Yeah, sometimes I forget we are living on a planet that is dynamic and changing all the time, and apparently we're floating through space. In the map below, a north arrow is superimposed on the map. The arrow is rotated based on the computed declination. Most maps include a title. The title is a powerful and staccato statement describing the purpose of the map. For example, observe chimpanzee mating sites, or sage-grouse distribution. The map title reveals important information about the intention of the cartographer. A map title, as it relates to a map, is very similar to an abbreviated thesis statement for a dissertation. A map title is usually a major map element that can be worded to show the map theme or the map content. A map title is an important component of virtually any map. But in addition to a map title, maps also contain annotation or other text features. This may include river names, lake names, or other features on a map. By employing different distinctions of font, style, color, and size, the lettering on a map can be used to show a variety of features. Within a GIS, a cartographer is often faced with a huge number of choices when planning for lettering on a map. Okay, so there's a bewildering variety of letter forms available to us. And the cool thing is that each one has its own personality. Let's take a look at font characteristics with hopes of using this information to help us design a good map. Choices in style, size, form, color, and placement are key in the design of a legible and organized map. Style, also known as font, refers to the actual geometric design of the letters. A font family is a group of fonts designed to be used in combination and exhibit similar characteristics. A few examples of font family names include Times New Roman, Arial, and Century Schoolbook. The activity of selecting the font family or type, preparing the names, and placing the names in position is often known as lettering on the map. A font family can take on many different forms, including italicized or bold. The form also refers to whether it is composed of capital and or lowercase letters. Other characteristics can be applied to a font family, including a size, a stretch, a weight, and a variant. The type size, which refers to the height of the type on a printed or on a digital page, is often designated by points. Apparently, the idea of points started when metal casting blocks were used for typefaces. The point size referred to the distance between the lower edges and the upper edges of the metal block. 1 point equals approximately 0.35 millimeters. When looking at 12-point type, the total distance would be approximately 4.2 millimeters. Keep in mind that map readers typically are not very sensitive to small variations in type size. Using our cartographic license, we can make variations in font size between 10 and 15%. These slight differences are pretty much unrecognizable. Having the ability or option to vary font size gives us more freedom in the placement of text. A font stretch indicates the desired amount of condensing or expansion in the glyphs used to render the text. Kerning is another word to represent the amount of space between characters. The weight refers to the lightness or boldness. If we look closely at the strokes that make up letters and symbols, we notice a variation in the details. A serif is a feature of the letter and appears at the end of the line or the stroke. As an example, let's look at the letter T in the Times New Roman font family. At the end of each line segment, there is a small hatch mark that hangs down, and this is known as the serif. The serifs represent a non-structural detail of the letters. A font that has serifs is called a serif font. A font without serifs is called a sans serif. Sans is a French word meaning without. Like all other marks on a map, the type or annotation is considered a symbol. And regardless of the type or kind of map we're creating, the lettering is there to be seen and to be read. As we generate our map and select type, we can be guided by certain general principles. These general principles have evolved over time. For example, ornate or fancy lettering is difficult to read, whereas a well-designed classic modern sans serif or serif font is often very easy to read. The thickness of the lines forming the letters can also dictate the readability of characters or lettering. Fonts with thin lines are relatively difficult to read, but they also have the advantage in that they can be used to annotate small features on the map. Thick, bold lettering may be easier to read and be seen, but they can also overshadow or obstruct other equally important data on the map. As a general rule, the fewer number of styles used on the map, the better. Style variations or differences in styles are often best used when differentiating different features on the map. As a general rule, use capital letters when emphasizing important names and titles on the map. There is a tendency in cartography to use slanted or italic lettering when labeling hydrography, landforms, and other natural features. Apparently, the use of italic or slanted lettering seems to suggest the flowing or fluidity of water. Establishing a great level of contrast between the lettering and the background that the lettering is on can ensure that our text will be readable. If the real estate behind our lettering has quite a variation in hue and or shading, we can use a halo around the lettering to increase the visibility. The placement of text on a map can make or break a cartographic product. Let's take a look at some general rules for the placement of text. And again, these are general rules, so they can be broken on occasion. First, lettering should never be upside down. If it's critical that text placement is vertical, lettering should be oriented to match the orientation structure of the map. In most cases, vertical annotation should be read from the bottom up. Placement of street annotation can sometimes be confusing and difficult. As a general rule, for text orientation along linear features, always read from left to right and read from south to north. Placing text above a line should be the highest preference, but if it's important for clarity, text can be placed below a line. Text should also be offset from a linear feature to allow greater readability. Try to put yourself into the map reader's perspective to determine if the text is readable. Don't just rely on what the GIS provides. Take some time to make modifications if necessary. Allowing type to follow the curvature of a feature can sometimes be beneficial, but type shouldn't be curved unless it's really necessary to do so. Text entities on the map shouldn't clash with each other. Relying on the GIS to place text for us automatically is pretty cool, but on occasion, manual text placement may be required to prevent conflicts. When using text to name a water body or a land feature, that text should be entirely on that feature. When placing a geographic name on a map that has a possessive form, such as Mary's Lake, an apostrophe may seem necessary, but it is discouraged on a map. Since its inception in the 1890s, the U.S. Board of Geographic Names has discouraged the use of this possessive form. The use of color on a map plays an especially important role in helping with map clarity. Even a small drop or two of color can really help with the appearance of a map. Color helps us simplify and clarify features as well as unify various map elements. Keep in mind that color is subjective and people respond to color differently. Overall, color allows us to generate more detail on a map. It can also add more visual clarity. Many cartographers use color because it increases the design possibilities. Light bouncing off a map act as particles like little bullets that stream directly from the source into our eyes. Light also acts like waves, little ripples in space. In the retina of the human eye, there are two different types of cells, the rod cell and the cone cell. These cells were named as such primarily because of their shape when viewed in a microscope. Apparently, in the human eye, there are more rod cells in the retina than there are cone cells. The retinal cones in our eye are the color receptors of the eye, and the retinal rod cells are not sensitive to color, but they are very sensitive to low light levels. So what does this have to do with a map? Because the perception of color stems from the varying sensitivity of different types of cone cells in the retina to the different parts of the spectrum, colors can be quantified based on how they stimulate these cells in our eye. The science of color, sometimes referred to as chromatics, includes the study of the perception of color by the human eye. Our eyes are more sensitive to certain hue values. The hues are also known as colors. These are just general observations. There are no precise indicators for everyone. In an unscientific study, most people rank hues in the following order. The first being the most sensitive to our eye. First red, then green, yellow, blue, and then purple. Some hues, or colors, are described as primary. Primary colors can be considered a set of colors that can be combined together to make a useful range of other colors. Additive combinations of colors include red, green, and blue. For a subtractive combination of colors, such as in mixing of pigments and dyes in our printers, we normally use cyan, magenta, and yellow. The dimensions of color, which include the hue, the value, and the intensity, all work together to stimulate a response in the cones of our eye. A map can employ colors in a great variety of ways. To reveal or show likeness of features, we can shade those features the same color. For example, on a world map, if we were to shade all of the oceans and seas the same color, they appear to be continuous and related. Color can also be used as a decorative element on a map. It can also be used to enhance or strengthen the purpose of a symbol. Over time, cartographic conventions have been established, and color use is often consistent across many different types of map. Let's review a few general conventions that have been used and established for and by cartographers. Blue is often used to reflect water or a positive numerical value, and also something that may be cool, such as a temperature. The hue of blue can be used for streams, oceans, rivers, and lakes. Greens are often used for forests, vegetation, lowland, or grassland areas. Greens can represent parks, golf courses, and orchards. Brown is used for mountains, hills, and other landforms, and are often used to represent contours. Brown is also associated with a dryland or desert and national parks. Yellows are often used to depict dryness or even distressed vegetation. In a map revealing elevation, it can be used to represent the intermediate elevation values. Yellow is sometimes used to represent cities or built-up urban areas also. Red is often used to represent important items on the map. It can also be used to represent roads, such as interstates, and cities. It also represents a feeling of warmth and can be used on a precipitation or temperature map to reveal higher values. Red can also be used for the representation of special interest sites, such as a map revealing threatened and endangered species. A single map should always use consistent colors. Purple is often used for roads or highways. It's also used on U.S. geological topographic maps to reveal features that have been modified or added since the map was surveyed originally. Black is often used for place names, buildings, borders, roads, and railroads. The design of a map begins with the consideration of the purpose of the map and of the relevant data available to create the map. As a map reader scans our map with their eyes, we want them to be able to digest the information fairly quickly and to learn the story we are trying to tell. A well-designed map should achieve goals of clarity, order, unity, visual contrast, balance, and a visual hierarchy. Clarity can be defined as, well, the mapmaker having a fairly clear understanding of what they're trying to represent on the map, which is also known as conceptual clarity. Visual clarity refers to the orchestration of all the graphic features on the map and how the cartographer translates the graphic features into graphic symbols on the map. When a map reader looks at our map, in many cases they follow a certain sequence or an order when viewing the components on the map. In many cases, they look for a title first, look at the overall schema or pattern of the map, and then refer to a map legend, and then look at peripheral data such as the author or maybe a locator map. In many ways, visual clarity refers to the metamorphosis of geographic features converted or translated into a graphic symbol on the map. By somehow utilizing the minimum amount of symbolization, we can achieve a visual representation of clarity. In terms of that famous beverage of wine, clarity often refers to the sediment or the cloudiness of the wine. If we can carry the concept of clarity from this alcoholic beverage over to a paper map, maybe we too can come up with a map that isn't cloudy to our users. Unity and harmony refer to how well these complex patterns on our map can be represented to look pleasing. Are the symbols, patterns, and colors kept consistent? Or is the map too complex and very difficult to digest? Visual contrast refers to how well symbols on the map are differentiated from one another. Visual contrast is one of the most important considerations when making a map. Does our map reveal visual contrast between lake features and landforms? By varying the weights of lines and the intensities of colors, we can make our map more interesting and easier to read. Most maps contain numerous elements to include a legend, a scale bar, a north arrow, graticules, and the main body of the map. We can achieve balance by positioning these map elements relative to a visual center of gravity of the map. It often takes time to experiment with different alternative layouts to come up with balance. The visual hierarchy of a map can be described as the method of placement of different map features so that the human eye-brain system can automatically separate the visual images and understand the thematic spatial content of the map. In terms of mapping, hierarchy is a system of ranking and organizing the map elements, where each element of the map is subordinate to a single other element. The ultimate goal is to make it easy for the map reader to focus on a particular layer or thematic layer and extract the information that they are interested in. We can accomplish this by making sure that the most important information on our map has the strongest visual impact. In addition, if we eliminate entirely unnecessary information from the map and then symbolize in a powerful way the important features on the map, by the way, we can accomplish this by making certain map elements bigger and using brilliant colors such as red or magenta. A big part of visual hierarchy is a concept called figure-ground relationships. Let's dissect the phrase figure ground. Figure refers to the object or objects on our map that really stand out. A map revealing water sampling locations can be emphasized somehow by using symbols which appear to stand out. Ground refers to the background of our map, and this is where typically our context information appears. One method of accomplishing figure-ground relationships is to utilize shading. In this example, the figure-ground relationship is not very clear. By applying shading to the lakes, the figure-ground relationship becomes clear. Let's review a few additional components or elements that can be placed on a map to promote effective cartographic communication. A locator map or a reference map often provides the map reader with an indication of where the main map is in relation to another larger recognizable location. In this simple example, we have a map that covers kind of a large-scale area. This large-scale area also represents a project area and is superimposed on the state of Montana. A simple glimpse of this locator map gives the map reader a general idea of where the project area resides. Most maps and the data comprising the maps represent a snapshot in time. Because we live in a dynamic world, things change. Some things change often, Others remain fairly static for a long period of time. A date can be used to represent numerous aspects of a map, including the date the map was created, and a date could reflect when information were collected for map features. Most well-written books have a reference section. In general, a reference is information that identifies a particular publication or the source of the information used for a book. Most maps should also contain a reference of some type, an indication of where specific information originated from. If data portrayed on the map was obtained from some governmental entity, specify the source and the date you obtained the data. If data presented on the map were collected with field instruments, including water sampling devices or GPS, specify that. Who authored this amazing cartographic product? Was it you? If so, be sure to place your name on the map and be proud of what you've accomplished. If the map was a collaborative effort, specify all the individuals that helped out on the map. A grid, which is made up of a network of evenly spaced vertical and horizontal lines, can help a map reader identify the location of a place. Another option is placing a measured grid on our map, where locations are echoed using projected coordinate values, such as state plane or UTM. Graticules, which are known as lines showing parallels of latitudes and meridians of longitude, can reveal geographic references on our map. The body of our map is comprised of those elements and map components that help us tell our cartographic story. The body is important. These map elements, which make up the map body, are used to communicate ideas to our map readers. The body of the map should be the dominant part of our map. By establishing visual clarity, visual hierarchy, and strong figure ground clarity, we can influence where the map reader focuses his or her attention first. Let's say you're making a map and you forget the important components that comprise a typical powerful map. Try to remember the phrase last dog. Why? Well, L for legend, A for author, S for scale, T for title, D for date, O for orientation, such as a north arrow, or an overview map or vicinity map, and G for grid. Over the past 40 minutes or so, we've covered some of the aspects of cartographic design. I encourage you to continue your quest in learning more about cartography. Read and review literature and books which focus on cartography and making maps. A map, or a graphic representation of spatial relationships, is a powerful way of communicating concepts to other people. One of the beautiful things about ArcMap is its inherent tools to help us along the path to create a powerful map. Hey, my cell phone's ringing. Let me grab this phone call. Hold on for a sec.
Hello, this is Jerry.
Hello, Jerry. This is Michael from the Breeze Power Company here in northwestern Montana. It's pretty windy up here today, though. How are you doing today, Jerry?
Well, I'm doing pretty well. Thanks for the call, Mike. How can I help you?
Well, Jerry, I'm from Breeze Power Company. We're trying to come up with some placements for the wind generation facility here in northwestern Montana. We're wondering if you can help us make a map that shows existing wind speeds up in Pondera County. That's spelled Pondera. Yeah, so if you can make a color-coded map that shows wind speed based on category, and also if you have access to power line information showing existing or proposed power lines, that would be really helpful too. Can you help us with this, Jerry?
Michael, thank you for the clear explanation. I appreciate it. Yeah, so I believe we can make a map for you. Let me make an attempt to gather the spatial data required to make this map, and if we can obtain the data, we will create the map.
That is just excellent. Thank you so much, Jerry. I really appreciate your time, and we really look forward to seeing the map. I'm wishing you a great day.
As a reiteration of what Michael said, he would like us to prepare a map for him reflecting existing wind speed information. Apparently, they are trying to find placements for wind generation facilities to generate electricity with wind power for an area in northwestern Montana, specifically a county called Pondera, Pondera. And if possible, he would like us to show existing or proposed power lines that run through that area. What do you say? Are you up for the challenge? Let's you and I make an attempt to create this map for Michael. To accomplish our mission, let's follow these simple steps. Let's make a list or a dream list of those geographic information assets that would be ideal for this map. Then we'll begin our research and make an attempt to obtain the said geographic information asset. Here is our list. Spatial data representing wind speed and wind power, specifically for our project area, and power lines. Those are the two primary components of our map. In terms of a figure ground model, the figures would be the wind speed and the power lines, the primary figures of our map, and the background would be supplementary information, including roads, place names, including towns, cities, rivers, lakes. We also need to reveal the extent of the project area, or specifically the county, namely Pend Oreille County.
Fast forward through time.
Excellent work. You have obtained the necessary data for us to proceed with our project. We must give great thanks to the Montana Geographic Information Clearinghouse, the website where we obtained all of this information.
nris.mt.gov/GIS.
If you wish to make a wind map for Pend Oreille County, here's a suggestion. Feel free to follow along or watch the tutorial and then use the knowledge you've gained to create your map. Here's our plan. First, we're going to use our catalog to explore the spatial data we've obtained. Then we will use ArcMap to create our map. Let's establish a folder connection to the Pend Oreille folder so we can view and utilize these spatial assets. I will click on Create Folder Connection and navigate to the Pend Oreille directory. After opening this new folder connection, I observe a single folder titled Wind. There also exists a geodatabase titled Pend Oreille GIS. After expanding the folder titled Wind, I observe two ESRI grids, wind speed and wind power. After selecting the wind power grid in the catalog tree, I'll make the description tab active. We can read the metadata that describes the spatial asset. In simple terms, this grid reveals an estimated wind power distribution based on a 400-meter pixel that represents the average power of the wind in watts per square meter at an elevation of 50 meters above the ground. After making the preview tab active, we observe this wind power grid looks more like a hillshade. After making the Identify tool active, we can click on a location on the map to obtain the pixel value of that cell. After making the wind speed grid active in the catalog tree, we'll click on the Description tab. This asset reveals wind speed distribution. Each pixel represents a 400-meter grid on the ground, and that grid stores a single value averaging the wind speed for that region. The average wind speed measured in meters per second was collected at a point 50 meters above the ground. After making the Preview tab active, I'll invoke the Identify tool and click on a location. The raster pixel stores a value that represents the average wind speed in meters per second. After expanding the geodatabase in the catalog tree, I observe 8 feature datasets including boundaries, geology, hydrography, public land survey, structures and facilities, transmission lines, transportation, and weather. The boundaries feature dataset includes information related to cities, counties, federal land, Indian reservations, land ownership, Montana counties, national forest boundaries, a national wildlife refuge, and other public land ownership. The geology feature dataset contains information on the continental divide and fault lines. The hydrography feature dataset includes information on lakes, rivers, and streams. Public land survey information appears to be stored in this feature dataset. Points representing weather stations are stored in the structures and facilities feature dataset. Michael had asked if we could place power transmission lines on our map. That data are stored in this asset titled transmission lines _FEMA. Highways and interstates are stored in the feature dataset titled transportation, and precipitation values are stored in the feature dataset titled weather. Let's review a few options for our map layout. After talking with Michael and his group, they indicated to me they'd like to use a landscape layout 11 inches by 8.5. They would like the map to be full color. They asked that the title state Pend Oreille County Wind Map. We will include a locator map showing where Pend Oreille County is within the state of Montana. The body of the map will reveal wind power distribution or wind speed, power lines, major cities and towns, transportation including interstates and major highways, and we will determine whether or not we can reveal hydrography. If it becomes overpowering, we may leave it off the map. Assuming a page size of landscape 11 inches by 8.5, here are a few options we could pursue. We could include a locator map in the lower right-hand corner, title at the bottom, along with a description of the spatial assets we use for the map. We could place a date stamp here, along with the author of the map. We could place a north arrow either in the body of the map or in this lower legend area. Because we have some blank space on the body of our map, we could attempt to place a legend in that area. Yet another option for our map layout would look something like this. Because we are working with a fairly small page size, we could try to maximize the body of our map and then look for extra space around the peripheral of the map and use that extra space as filler for our legend, title, north arrow, and other map elements. These are only ideas for our layout. As we compose our map, we may come up with a completely different alternative. I've opened a fresh copy of ArcMap. Fresh, and actually it does smell a little bit like raspberries. Let's open up the ArcCatalog window and first find out where Pend Oreille County is. After opening our folder connection and the geodatabase housing our vector data, I'll expand the boundaries feature dataset and drag the asset titled County Poly to our map display. This spatial asset is automatically placed in our single active data frame titled Layers. Let's locate Pend Oreille County. After making the Find tool active, I'll type in the phrase Pend Oreille and then tap on the Find button. In the bottom of the Find dialog box, we see ArcMap found one object, the value Pend Oreille. Let's right-click on the name Pend Oreille and request that ArcMap zoom to that feature. Let's close the Find dialog box. I will press and hold the X key on the keyboard to temporarily invoke the Zoom Out tool, and then roll the mouse wheel back to zoom out. Now we know where our project area is. Because this spatial asset titled County Poly shows the entire state of Montana and our project area, I have an idea. Let's use our active data frame titled Layers to represent our Vicinity Map. Let's rename the active data frame currently titled Layers, Vicinity or Locator Map. Using the mouse, double-click on the phrase Layers, which invokes the Data Frame Properties dialog box. After making the General tab active, I'll type in a name of Vicinity Map, and then click OK, because you know what? Everything is OK. Now we'll need to add an additional data frame to house or store the body of our map. From the main menu, choose Insert Data Frame. It becomes the active data frame. Note the bold text. I will double-click on this new data frame in the table of contents and enter a name of Pend Oreille Wind Map, and then click OK. Because this is the active data frame, it will be the recipient of all spatial assets we drag into ArcMap. I'll select the ESRI grid wind power and drag it to ArcMap, and also drag wind speed as well. From the Pend Oreille GIS geodatabase, specifically the transmission line feature dataset, let's add to ArcMap transmission lines underscore FEMA. We will also add the interstate highways from the transportation feature dataset and communities or cities. Let's save our map project, File, Save. After navigating to the Pend Oreille directory, let's enter a name, Pend Oreille Wind Map, and then a date, and I'll enter version 1 or V1, and then click Save. Our map project contains, for the most part, the spatial assets we will be using to create our map. Upon adding these spatial assets to ArcMap, ArcMap automatically assigned a symbol and a color to represent those features on our map. To gain more real estate, let's pin the ArcCatalog window to the ArcMap interface. Auto-hide by clicking on this push pin. In the table of contents, let's rearrange the data frames. So the Pend Oreille Wind Map data frame is on top or above the Vicinity Map. Click with the left mouse button on the data frame and drag, release the mouse. Next, I will adjust the map extent so that our project area occupies our map display. Using the mouse, either right-click on Wind Speed or Wind Power, zoom to layer. Let's add to our main map a spatial asset representing the county boundaries as a polygon. Quite possibly the easiest way to accomplish this mission is to drag the asset from our Vicinity Map to the main map. Click, drag. Next, we will change the symbology of the county polygons so we only see the outline of the county. Invoke the symbol selector by double-clicking on the symbol below our polygon layer. From the symbol selector, we will choose the hollow symbol here, and then we'll choose a different color and then apply these changes. Let's create a bookmark so we can easily come back to this map extent. From the main menu, choose Bookmarks, Create. I will enter a bookmark name of Primary Map Extent. These spatial bookmarks can be useful in that the bookmark identifies a location, a geographic location that we want to save and reference later. So for example, if we zoom out or zoom to another area, we can easily come back to this exact same geographic extent by reinvoking this bookmark. Did you just see what I saw? In that our transmission line asset covers the entire US? Let's zoom out to the full extent of the transmission line asset. Right-click, zoom to layer. Though we only need a small part of it. Let's generate a subset of this layer. This new subset will contain only those transmission lines that lie within the state of Montana. Do we have to do this? No, not necessarily, but I think it'll make things a little cleaner. Imagine you're in a cave and you have to draw all of these power lines on a rock wall using raspberries. Now that would be a waste of raspberries. We will be using an analysis tool called Clip to help us through this process. The Clip tool will extract those transmission lines that are in the great state of Montana. To get started, we will open the search window and then type in the phrase Clip. To initiate the search, we'll click on the small magnifying glass. There it is, the tool titled Clip Analysis. After double-clicking on the hyperlink as part of this tool, that tool will be revealed in its toolbox. Here it is. To invoke the Clip tool, double-click on it here. The input feature, we can select from this drop-down list, transmission lines _ FEMA. It is the master layer that the Clip will grab information from. The Clip features will be the state of Montana. This will be our cookie cutter or our power line cutter. The state of Montana polygon layer is stored in the boundaries feature dataset. Let's see if we can find it. Select State of Montana and click Add. The name of the output feature class will be Transmission Lines Montana. We will place this new spatial asset in the feature dataset titled Transmission Lines. I will enter the name of our new feature class. Perfect. After clicking OK, ArcMap begins the process of clipping from the master transmission line _ FEMA asset. The scrolling blue text in the status bar indicates the process is still ongoing. Upon completion of the clip operation, the newly generated asset is added to ArcMap. To clean up our display, let's auto-hide the catalog and search windows. Let's set our spatial extent to the new transmission asset we generated. Right-click, zoom to layer. Let's remove from the table of contents the spatial asset representing transmission lines for the entire U.S. Right-click, remove. After opening the attribute table for the transmission lines residing in Montana, we observe an attribute field titled KV. At first glance, it appears as if this field is populated with a value of 115, though if we right-click on the field and choose Statistics, we see that there are other values. Let's attempt to symbolize the transmission lines based on their internal attribute. For example, we could weight the line symbols based on the capacity of the line. A line with a higher capacity would have a thicker symbol compared to a line with a lesser capacity. Yeah, and by the way, kilo, as in kilovolts, is a unit prefix in the metric system denoting multiplication by 1,000. 1 kilovolt is 1,000 volts. Most home appliances use about 120 to 240 volts. High voltage electric power transmission lines have a carrying capacity of about 110 to 115 kilovolts. Let's change the symbols used to represent the transmission lines. Double-click on the asset name in the table of contents to invoke the Layer Properties dialog box. Make the Symbology tab active and click on Categories. Our value field will be KV. I'll select that here and then click on Add All Values. We'll look at a couple options for symbolizing our transmission lines. In this example, we will manually select both the weight and color of the lines. We begin by double-clicking on the existing symbol for the highest value, 500. We will select this symbol initially and change its weight value. Set the size to 5. We'll repeat the process for the next victim. I will enter a width of 4. The next value will have a weight or width of 3. For the last KV item, we will enter a weight value of 2. Yet another option is to use an automated graduated symbol based on quantities. We won't be using this method as it doesn't really fit our project, though it does assign automatically a series of weighted symbols. Choose Quantities, and then click on Graduated Symbols. Choose a value of KV. Choose Classify, and then ArcMap automatically assigns weighted symbols based on natural breaks in our data. Again, this doesn't really fit our project, so let's go back to the graduated symbols we developed manually. I'll click on Unique Values, and then apply these changes. Let's reestablish the map extent from our bookmarks and save our project. If we open the attribute table for the asset representing counties, it appears as if the county name is stored in this field. Let's instruct ArcMap to automatically label each county polygon with this text phrase. After opening the Layer Properties dialog box and invoking the Labels tab, we'll place a checkbox next to the phrase Label Features in this layer. ArcMap determines the first field in our attribute table that contains a text field and sets that to the label field. We'll keep the font set to Arial and then change the size, 14. Change the font to bold by clicking on the B. We may need to revisit the size of the annotation based on how our map looks. We are currently in the data view mode, a great place to be as we compile the assets, which will eventually be a part of our map. Let's begin to design and lay out our map. We toggle to the layout view by clicking on this small icon. Our initial goals are to first adjust the page size and orientation, and adjust the data frames, which represent the two components that will comprise our map. First, we'll adjust the page orientation. From the main menu, choose File, Page, and Print Setup, and we'll place a radio button next to Landscape, and then click OK. Let's adjust the position and size of our vicinity map. With the Select Elements tool active, I will click within the data frame titled Vicinity Map, place the cursor on one of the handles. Note the change in the appearance of this cursor. Click and hold the left mouse button down, and drag the mouse to change the size of this box. Place the cursor in the box. Again, note the change in the cursor's appearance. Press and hold the left mouse button down and reposition this data frame to the lower right-hand corner of our map. With this data frame active, we'll click on the Full Extent tool, make the Select Elements tool active again. Next, we'll make the Pend County Wind Map data frame active by clicking inside of it. Let's reposition and resize this data frame and reestablish our predefined map extent. To add a north arrow, from the main menu, choose Insert, North Arrow. I will select this north arrow. Fine-tuning will readjust the size and its position. To insert a title for our map, from the main menu, choose Insert, Title. We'll enter Pend County Wind Map, and then click OK. After repositioning the title to the lower part of our map, the title shows up as a pretty small blob on our map. Let's change its size. This element is the active element. Notice the light cyan dashed box around the element. To change an aspect of this element, double-click on the element with the mouse. Click Change Symbol. One option is to manually adjust the font and size using the dialog controls placed on the right side of this panel. Instead, we will select the pre-established font size with the name of Map Title A Size. Click Apply and OK, and then we will reposition the title so it is centered on the bottom of our map. Our page layout, sometimes referred to as a map layout, is currently comprised of multiple elements, including 2 data frames, a title, and a north arrow. As we begin working on our map, one of the most common ways of inserting additional elements into our map, including a scale bar or additional text, is to choose Insert from the main menu. As we add more elements to our map, we refine these elements by editing their properties, which can include their position, size, and rotation. As a tip, you may wish to initially view your map layout in draft mode. The draft mode provides a very simplified view of the elements which comprise our map, and can often be useful in helping us find a placement for each element. To toggle to draft mode while in the layout window, right-click on the layout window and then choose draft mode. Each unique element on our map has a name used to identify it. We are now in draft mode, and notice that each element is drawn with the hollow frame, and the name of the element is placed inside that frame. Each element on our map by default is given a default name, though we can change an element's name to something unique and meaningful by invoking the Data Frame Properties dialog box and then clicking the General tab. For example, if we wanted to change the name of our existing vicinity map to something more meaningful, such as State of Montana Vicinity Map, we would follow this simple recipe. With the mouse, right-click on the data frame, choose Properties. After making the General tab active, we'll enter a new name here, and then apply these changes. Let's toggle out of draft mode and establish a locator rectangle on our vicinity map reflecting the extent of our Pend Wind Map. As a result, the extent of our main map will be displayed on the vicinity map. After making the State of Montana Vicinity Map data frame active, right-click, choose Properties, and then make the tab titled Extent Indicators active. Our goal is to show the extent of the Pend Wind Map data frame superimposed on the vicinity map. To accomplish this, we'll add the data frame Pend Wind Map to this right panel by clicking on the greater than sign. To change the frame's appearance and color, click on the Frame button, adjust the border and size, click OK, and then apply these changes. Saving our project is pretty important. I'm going to save our current project with a new suffix of V2 for version 2. Michael's request was for a map showing wind speed calculations around Pend County. Let's zoom in a little tighter to show Pend County at a larger scale and establish a new bookmark for future reference. Because the extent indicator frame on our vicinity map is dynamically linked to our main map, it is updated automatically. In our current map composition, the Pend County Wind Map fills its current data frame. The process of clipping a data frame affords us the opportunity to create a data frame in a shape other than a rectangle. For example, we could clip our existing data frame to be an oval or circle. This clipping process is not a destructive process in that it doesn't change or modify our data in any way. Upon clipping a data frame, both map content and labels respect this new shape. For example, if we wanted to clip our data frame using an ellipse, we begin by adding the Draw toolbar to our interface. Right-click in the blank space here and choose Draw. I'm going to dock this toolbar to the interface. Activate the Ellipse tool from this pull-down list. Place the cursor on the screen and then draw the ellipse. An interesting aspect of this ellipse is that it is partially non-toxic and it glows in the light. I'll make the Select Elements tool active from the Tools toolbar and grab or select that circle graphic. It is critical we select the element that will become our mask or clip. If we wanted to clip the data frame housing our main map, we would right-click on that data frame and choose Properties to invoke the Data Frame Properties dialog box. Make the Data Frame tab active. Focusing on Clip Options, we invoke the drop-down menu and select Clip to Shape. Click on Specify Shape and place a radio button next to Outline of Selected Graphics. Instead of proceeding with this data frame clip, let's instead clip the data frame based on the true shape of Pend County. Let's get out of this, hit Cancel, Cancel, and then with the ellipse selected, I'll tap on the Delete key. In order to clip the data frame based on the shape of Pend County, we need to select Pend County. With the Select tool active, I'll click on Pend County. Notice the thin cyan outline, indicating Pend County is the selected feature. Double-click on Pend Wind Map data frame in the table of contents to invoke the Data Frame Properties dialog box. Once again, make the Data Frame tab active. Under Clip Options, we choose Clip to Shape. Click on Specify Shape. Place a radio button next to Outline of Features. Then we choose the layer, County Poly, which will act as our clipper. Under the Features pull-down, we choose Selected. Because Pend County is selected, its outline and shape will dictate how our data frame is clipped. Click OK, and then Apply. We observe that our Vicinity Map is updated, as is the main map. One advantage of clipping a data frame based on a selected feature is we can isolate regions, though in my opinion, it is nice to see a region and its surrounding area. If we decide we want to remove this clip data frame based on Pend County, in the Data Frame Properties dialog box with the Data Frame tab active, under Clip Options, we would choose No Clipping and then apply these changes. We should also clear selected features by clicking on this icon here. One huge advantage of clipping a data frame based on a selected feature, such as Pend County, is that we do not need to use the analysis tool called Clip, found in our toolbox, to clip all of our vector assets. In previous versions of some GIS software, it was necessary to create an entire new data set based on this outline, such as Pend, in order to achieve the effect we just observed with clipping the data frame using a selected feature. Another option we could pursue is to isolate Pend County using a mask. The cool thing about applying a mask is that the mask doesn't necessarily have to take on this draconian, absolute, definitive masking of everything outside of the area of interest. Instead, this mask could have a level of transparency, allowing the surrounding region to kind of bleed through a little bit. Are you set for the challenge? Let's begin to create a mask for Pend County. First, I will save our current project and then start a new project. From the main menu, choose File, New, and we'll select a blank template. Toggle to Data View, unhide our catalog, open the feature dataset titled Boundaries. We will be making a duplicate copy of the existing asset titled County Poly. To duplicate this feature class, right-click, select it, choose Copy. To place a copy in the Boundaries feature dataset, right-click on that feature dataset and choose Paste. A copy is being generated. The name of the new feature class is called County_Poly1. Let's rename it by right-clicking on it and choosing Rename. Its new name will be Pend Mask. Let's add this new asset to ArcMap by dragging it from Catalog to ArcMap. In simple terms, we will be deleting Pend County from this mask. In other words, this spatial asset will contain all of the Montana counties except for Pend. We'll need to begin an editing session. Click on this icon to initiate the Editor toolbar. From the Editor toolbar, Edit, Start Editing. Make the Edit tool active by clicking on this small solid arrowhead. Click on Pend County to select it. To delete Pend County, from the main menu, choose Edit, Delete, or click on the black X here. This black X is evil. It's like the Grim Reaper. I mean, it totally wipes stuff out. That's it. We're done. Except we do need to stop the editing process. From the Editor toolbar, choose Editor, Stop Editing, and save our edits. Let's remove the Editor toolbar from the interface by clicking on this X. We've created the mask for Pend County in this untitled map. We no longer need this untitled project. Let's reopen our main project. From the main menu, choose File. Note that at the bottom of this list, there appears to be a series of maps that were previously open. We'll select number 1. We will not save changes to the untitled project. Using the Add Data button, we'll navigate to the feature dataset titled Boundaries and add to our project the asset titled Pondere Mask. To change its color to black, we double-click on the symbol below Pondere Mask. This invokes the symbol selector. I will select this solid black symbol, click OK, and apply. Next, we'll set the transparency of Pondere Mask. We'll open the Layer Properties dialog box by double-clicking on Pondere Mask in the table of contents, clicking on the Display tab, and setting the transparent percentage to 60%. As a result, Pondere County seems to be glowing and isolated, though the surrounding area and map features are still visible. We could experiment by creating a white mask. After invoking the symbol selector, I will search for a white symbol by typing in white, select the symbol, and apply. Next, let's adjust the symbols used to represent the wind speed grid. After clicking on the small plus sign to the left of the wind speed image, it appears as if the wind speed categories have been assigned random colors. Let's assign colors based on a color ramp. The color ramp will have green on one end of the spectrum, yellow in the middle, and red at the other end. Let's open the Layer Property dialog box by double-clicking on this item in the table of contents, and then we'll click on the Symbology tab. Currently, the mode for drawing the raster and assigning a color is based on a unique value. There are 16 unique values. Sure, we could keep all 16 items in our legend, though apparently the human eye-brain system has a tough time discerning differences in a legend if there are more than 7 items that comprise the legend. That being said, we will be designing the legend to represent the wind speeds so that it has 7 or fewer items. Using a graduated color ramp, the visual contrast may lead to perceptual differences. Limiting the number of categories to 7 may help the eye discern the differences. So instead of using unique values, we will be using classified values. We'll click on Classified here. Choose this color ramp, and then change the number of classes to 7. These 7 classes are based on natural breaks using the Jinx method. If we wish to modify the classification, we can click on the Classify button, specify a different classification method from this pull-down list, and adjust the snap breaks to data values by using the mouse and the slider bar. We are presented with a symbol, the wind speed range, a category that will be represented with this symbol, and then a label. The label is important. The label is what will appear on our legend. We will modify the label values so they have more visual clarity. We'll modify each one of these so that we have a number, a dash, and then another number without decimal point. For example, 0-3. I will proceed with modifying the rest of the label entries. Recall that the metadata states that the measurements of the wind speed are in meters per second. These samples were taken at an elevation of 50 meters above the ground. On our legend, it would be nice to show both meters per second and a wind speed in miles per hour. We can perform the conversion between meters per second and miles per hour pretty easily. 1 meter per second equals approximately 2.23694 miles per hour. All right, after updating the label values, we'll apply these changes and click OK. Next, let's add the legend to the map. It appears as if we have adequate space for the legend in the lower left-hand corner of our map frame. Before we add the legend, let's add a small rectangle to the lower left-hand corner of our map display. Change its color to white, and that rectangle will mask out the map information, and then the legend can be placed on top of the mask. To accomplish this, we'll make the rectangle tool active. From the drawing toolbar, place the cursor on the screen, click and hold the left mouse button, and draw the box. This element is selected, and if we double click on it, we can choose the fill color. Instead of using the yellow fill, let's choose a symbol with a white background. We'll click on Change Symbol, and I'll type in white in the search area, and select this symbol titled Snow. Click OK, then Apply. To insert the legend from the main menu, we'll choose Insert Legend. 2 panels appear. On the left panel, we see the map layers. The right panel displays those items that will appear as legend items. To remove an item from the legend list, we select it, for example, wind power, and then click the small arrowhead to the left. I'm going to remove all legend items except for wind speed. On this map that we are creating, the wind speed information is primary. Therefore, let's create a primary legend to echo wind speed information. Eventually, we will create a secondary legend to reveal information on power lines, roads, and cities. Click Next. For a legend title, let's enter wind speed. We will accept all of the other default values for the legend wizard by clicking on Next multiple times. Then click Finish to finalize this wizard. To reposition and scale the legend to fit within the rectangle box, use the handles on either of the 4 corners of the legend. Let's save our project, File, Save, and add the Layout toolbar to our project. Right-click in this blank space, select Layout. Let's dissect the layout toolbar. It's important to remember that the layout toolbar differs from the tools toolbar. Sure, they both have a zoom in tool and a zoom out tool and a pan tool, though the layout toolbar is designed to work specifically with our map layout. The zoom in tool on the layout toolbar affords us the opportunity to zoom into our map layout. We can either click on any part of the layout to zoom in, or we can drag a box to zoom into a particular part of our map. If we focus on the layout toolbar, note that most of the tools are active. If we toggle to data view, they become ghosted or gray. A shortcut to zoom in or out is to roll the mouse wheel forward or backward, or hold the control key down to fine-tune the zooming operation. A shortcut is to press and hold the Z key to temporarily gain control of the zoom in tool. The zoom out tool, the tool that appears as a magnifying glass with a little piece of paper behind it, zooms out of our layout. Again, it too will be disabled if we are in data view. In addition to using the roll wheel on the mouse, we can temporarily turn on this tool by holding the X key on the keyboard. The pan tool, the tool with a hand with a piece of paper behind it, gives us the opportunity to pan the map's layout. Place the pan tool on our layout and move the mouse in any direction with the left mouse button depressed. To temporarily turn this tool on, we can press and hold the C key on the keyboard. The tool represented with an icon and 4 small arrowheads will zoom in to the whole page. In other words, it zooms to the full extent of our map layout and provides a complete view of our map. A shortcut to zoom into the whole page of our layout is to tap on the Insert key. The tool represented with a 1-to-1 proportion zooms to 100% of our layout. The purpose of this tool is to let us work on our map layout at approximately the same scale that it would be printed at. The fixed zoom out tool will zoom out on the center of our map layout. A quick shortcut is to tap on the minus key on the keyboard. We can either go back to or go to the next extent in our layout. The zoom to % display provides an opportunity to zoom to our map layout based on a percentage we either enter or choose from a drop-down list. Toggling to draft mode can be achieved by clicking on this button. We can focus on the data frame by clicking on this tool titled Focus Data Frame. The purpose of this tool is to place the active data frame into focus, meaning it will be the recipient for any graphics, text, or elements we add on top of it while we are in the layout view. Templates provide a quick way to generate a map. This tool, called Change Layout, lets us change our current layout by choosing a different template from a list. After we generate our map by hand, we will attempt to look at other options and other layouts. When using templates, ArcMap tries to arrange data frames and titles to the best of its ability. This tool, titled Data-Driven Pages Toolbar, this tool helps us generate a multitude of output pages by working with or taking a single layout and creating these multiple pages over a variety of different map extents. To customize the layout toolbar, to either add or remove tools, click on the small arrowhead to the left of the X and choose Customize. After making the Commands tab active, locate, for example, the command you wish to add to the toolbar, select it from within the Commands entry, and drag that tool to the toolbar. Using the Zoom In tool, I'll draw a box around the existing legend so we can see it with greater clarity. To add the phrase legend to the top of this box, insert text. I'll type in the phrase legend. Let's make the phrase legend stand out. We'll convert it to a bold font, double click on the phrase legend, and then tap on the Change Symbol button. This will invoke the dialog box, allowing us to change the font's characteristics. We'll change the size to 14, strengthen its appearance by making the font bold by clicking on the B. Yeah, that looks pretty good. And then we'll accept these changes by clicking OK, Apply, OK. Let's make some modifications to the legend. I don't necessarily like the name of the image or grid displayed in the legend, namely windspeed.img. Instead, let's rename it to something such as wind speed. If we double-click on that asset in the table of contents, click on the General tab, we can enter a new layer name, such as wind speed. Apply, OK. Now we don't need two titles saying wind speed. To remove the phrase wind speed from the legend, double-click on the legend in our map, click on the Legend tab, and then uncheck the box next to Show Legend Title. Apply, OK. In addition to showing wind speed in meters per second, we would also like to show wind speed in miles per hour. Using a calculator and notepad, I created this file. I also placed a copy of this text file in the Lesson Data folder. This is a simple text file showing ranges of values in miles per hour. We're in Notepad. We want to select all the text and then paste the text into ArcMap. From the Edit menu, we'll choose Select All or hit Control-A, and then Edit Copy or Control-C. After making ArcMap active, we'll insert this new text into our legend. Insert Text. The phrase text appears on our map. Select it and hit Control-A, and then tap on Control V to paste the mile per hour conversions into this text box. We'll need to change the font size so it matches the existing font size in the legend. Double click on this blob of text, click on Change Symbol. We'll set the font size to 8 point, apply these changes, and set the leading value to 4, which will space out each line to match the lines in the legend. Depending upon the size of your legend and its placement, you may need to adjust this value. Next, we'll insert another text phrase echoing MPH for miles per hour. MPH also stands for maps per hour. It can take an hour or more to create a decent map. We will place this MPH phrase above the newly created second column we just created. Next, we will enter a phrase abbreviating meters per second, insert text. We'll type in the phrase M/S, and then reposition next to the phrase value. Because the wind speed measurements were made at 50 meters above the ground, let's change the title to say wind speed at 50 meters. Double-click on wind speed in the table of contents. From the Layer Properties dialog box, make the General tab active, and we'll enter at 50 meters. Apply and OK. To zoom out to the whole page or the full extent of our page, we'll click on this tool called Zoom Whole Page. Before we add the secondary legend, let's adjust some of the symbols used to represent other features on our map. Starting with the interstate, to change its symbol, we double-click on it in the table of contents. Ideally, we would be using a symbol called freeway. Because we have power lines on the map, and these power lines are of importance to our map audience, let's use a more subdued symbol. In other words, we want the symbol used to represent the freeways to vary drastically from the symbols used to represent the power line. Let's use this subdued symbol, titled boundary, state, to represent the roads or interstates. Next, we'll change the color used to represent communities or cities, and this color should not conflict with the colors in our wind speed legend. Purple. Purple it is. To label the cities or communities on our map, invoke the Layer Properties dialog box by double-clicking on Cities in the table of contents. Make the Labels tab active. Place a checkbox next to Label Features in this layer. The label field will be Name. Set the font size to 9. We'll keep the color as black. On our map, let's label each transmission line with its kilovolt value. Double-click on Transmission Lines Montana in the table of contents. From the Layer Properties dialog box, make the Labels tab active. The label field will be KV, font size of 8, italic. Let's review the placement properties for this text. We verify that the value will be placed above the line, parallel to the line, remove duplicate labels, and the location will be along the line at best. And we cannot forget to place a checkbox next to label features in this layer. OK, apply, OK. Let's take a closer look at the annotation we just placed on the map. I'll make the Zoom In tool active from the Layout toolbar and zoom into this area. Some map readers may be a little confused reading a number adjacent to a transmission line. Let's append the two letters KV to this text phrase. In other words, the results in this case would be 115 space KV. The hope is that this suffix would provide clearer, more direct data to the map reader. To begin, we double-click on Transmission Lines Montana to invoke the Layer Properties dialog box. The current label field is a text string containing values of kilovolts. To add the suffix KV, we click on this expression button. In the expression box, we'll type space, ampersand. The ampersand sign corresponds to and, space, double quote, space, and then the two letters KV, and then end quote. Click OK. We observe that the two letters KV have been added to or appended to this text label. Let's add a simple description to our map, providing a summary of the wind speed information. We have room for this information in the lower right-hand corner of the map. Let's zoom in to the lower right-hand corner of our map using the Zoom In tool on the Layout toolbar. Then we'll make the Rectangle tool active and draw a rectangle, which will eventually be the container for this summary information. In an attempt to strike up a balance with our Vicinity Map, we will attempt to make a box about the same size and shape as the box in our Vicinity Map. We'll change the color of the box to white, double-click on the box, click on Change Symbol, and again we'll use the snow symbol, apply and OK. We will gather the summary information from the metadata tied to the wind speed grid. We will unhide our catalog.
Hello, our catalog. Come on out.
To view the summary of this asset, using the mouse, right-click on the grid titled Wind Speed and select Item Description. Using the mouse, we will select the first few sentences as part of the summary paragraph. Right-click on the selected text and choose Copy. close the item description dialog box. We will be adding text to a rectangle, in other words, rectangular text. As a result, text will be forced into that rectangle. To access the tool, click on the small arrowhead to the right of this A and choose Rectangular Text. And then draw a box where we want the text to appear. After double-clicking on the box, we can place our cursor in this box, titled Text, remove the phrase text, and hit Ctrl-V on the keyboard to paste the text we copied from the metadata. After clicking Change Symbol, we'll enter a font size of 8 and change the style to italic. Click OK, Apply, and OK. It's evident that the text doesn't quite fit, so we have a couple of choices. We can make the font smaller or make the box bigger. Because our page size is pretty small, let's make the box a little bigger. I'll select the white box. Using the handle, I'll drag it to the left. Select the text box, drag it to the left. That looks better. We'll add a title to this box, stating that this box contains a summary about the wind speed information. From the main menu, choose Insert Text. Double-click on that text box and type in the phrase Wind Speed Summary, and then reposition that text top center. Then I will zoom out to the full extent of our map page. Let's save our project and give it a new version number, version 3. Next, we'll add the secondary legend. The purpose of the secondary legend will be to echo information to the map reader on transmission lines, interstate highways, and cities. Prior to invoking the legend wizard, which is the tool that helps us create the legend, we have to focus on the table of contents and make sure that the appropriate data frame is activated. 2 data frames exist on our map. If the Vicinity Map data frame was active, remember we can toggle between data frames by hitting Control-Tab. The legend wizard would only be able to use the assets in that active data frame. Let's confirm that the Pondere Wind Map data frame is the active data frame. We'll make a slight modification to how the transmission lines will be represented in the legend. We want to remove the phrase all other values. To do this, double-click on transmission lines in the table of contents. Click on the Symbology tab, uncheck the box next to all other values. As a result, the small line and the phrase all other values will be hidden in the legend. All other values will be hidden on the map as well. We will change the layer name so it is a little easier to read. Click on the General tab and we'll enter Transmission Lines. Click Apply and OK. Here is our plan for generating the secondary legend. We will use the legend wizard to help us generate the first rendition of this secondary legend. The legend will be somewhat crude. Then we will modify the way the legend looks and also choose a placement for the legend. Though I'll leave it up to you as to where you think the legend should be placed. From the main menu, choose Insert Legend. Focusing on the panel to the right, titled Legend Items, our goal here is to retain only those items we want on our legend. So I'll remove the items we do not want to show, including the wind power grid, county poly, Pondere mask, and wind speed at 50 meters. The remaining items will appear on our legend. The title of this legend will be Legend. Click Next to continue. If we want to change the shape of the patches used to represent either line or areas on the legend, we can accomplish that from this window. So for example, if we wanted to change the patch used to represent cities, we would select that item, select the patch that you want from this list. Another option is to create a custom shape. We'll choose Urbanized Areas. Click Next, then Finish to complete this first rendition of our draft legend. After creating and viewing this initial legend design, we will then modify it so it melds or integrates well into our map. Alright, our draft legend has been placed on the map. I will isolate the legend by moving it to the left of our existing map frame, then zoom into the legend. Using the mouse, or if you have a gerbil or rat, that would probably work well too, double-click on the legend to invoke the Legend Properties dialog box. Initially, we will make the Items tab active. If our legend contained a wide array of information, we could create multiple columns to house that information. The process of creating multiple columns is pretty easy. Select an item, place a checkbox next to Place in New Column, and then specify the column number that we want that item placed in. We will keep our 3 legend items in one column. Next, we'll add a frame. We'll click on the Frame tab and enter a thin frame with a thickness of 1 point. If we click Apply, we see that the frame hugs the legend pretty tight. There isn't very much room between the legend items and the edge of the frame. To modify this, we'll enter a gap for both an X and Y value. For the X, we'll enter a gap of 12, and for Y, we'll enter a value of 6 points, and then apply. That looks better. We could place the legend in the lower left-hand corner below the main legend and resize it. Another option would be to extend the existing rectangle mask behind the main legend and add the secondary legend to the right of the main legend. Let's try that. With the Select Elements tool active, we'll click on the white mask box, grab one of the green handles on the right side, click with the left mouse button, and extend the size of the box. With the Select Elements tool active, click on the secondary legend, click and hold the left mouse button, and drag the legend into the secondary box. We do not need the phrase legend to appear twice. Let's remove the phrase legend from above the secondary legend. Double-click with the mouse to invoke the Legend Properties dialog box. After making the Legend tab active, we will uncheck the box next to Show Title. Click Apply and OK. Next, we'll add the logo for the Breeze Power Company. No, not their company jingle or song. We want the logo, the graphic logo. From the main menu, choose Insert Picture, and then browse to the directory Logo and select Breeze Power Company Logo, a JPEG file. Click Open. Grab one of the handles on the edges of the logo, resize, reposition. We will add a date reflecting the date the map was created. Insert text. It can be somewhat challenging to locate text after it's been inserted. If we right-click in the data frame and choose Toggle Draft Mode, there it is. We'll make it active. Double-click and enter today's date. We could also enter a date or a series of dates reflecting when the geographic information assets were created. I believe the wind speed information was generated in 2002. We'll enter the author, insert text, author name. I will enter the phrase map created for Breeze Power Company by KnowGIS. And then place the text on the map. Insert a scale bar. Insert scale bar. We'll select a standard scale bar. To change the units on the scale bar to reflect miles, click on the Properties button, set the units to miles, and place it on the map. I'll place a scale bar below the existing legend. There isn't a lot of room beneath our legend. We'll need to make a few adjustments. First, I will adjust the size of the mask. In an attempt to select all of the legend items, I will draw a selection box around all of these items, and then grab them as a unit and move them together. After these items are selected, let's group them together so they become a grouped element. They will be treated as one object. Right-click on the selected elements and choose Group. Let's take a little bit of time to adjust and resize the elements that make up the legend. This certainly is a delicate operation. We have to make sure we have the correct element selected. Zooming into the area of interest most certainly can help us with this activity. After toggling out of draft mode, I see we need to make another slight adjustment to the legend mask box so Padre County isn't obscured. This is a draft map, and we expect to come back and make adjustments, fine-tuning the placement of objects, including the legend. A grid comprised of a network of horizontal and vertical lines can be useful to a map reader in identifying locations on the map. Let's add a reference grid. From the main menu, we choose View, Data Frame Properties. Click on the Grids tab, then select New Grid. Place a radio button next to Reference Grid, which will divide our map into a series of reference grids. The name of the grid will be a reference grid. I'll enter that here. Click Next. In establishing the appearance, we'll keep the grid and index tabs and establish 5 columns and 5 rows for our intervals. Click Next. The tab type will be a rounded tab. Color, we could adjust the color of the tab here, such as a light gray color. Choose Next and Finish. Click OK. After the grid has been placed on our map, we may need to perform a little bit of cleanup. Let's scan for issues or problems. It's important to remember that the Grids tab can be used to add a new grid to our map, and it provides options to manage existing grids in Graticules for a data frame. It doesn't appear as if our newly added grid disturbed our map very much. We will need to reposition the Vicinity Map. Let's insert the phrase Vicinity Map below our Montana Vicinity Map. After inserting this text phrase, we'll continue looking for any other issues or problems. I think overall it looks okay, at least for our first round or draft map. This is a draft map. Our goal is to provide the map to Michael and his crew, have them review the map, and provide suggestions for change. Let's stamp our map with the phrase draft, so the map readers will know it is a draft map. Insert text. Once again, it becomes somewhat of a challenge to locate the text we just inserted. The small text box appears to be at the center of our map. I'll move it outside the map frame. To adjust the text properties, we'll double-click on this new text item, enter the word draft, and then click Change Symbol. and make it fairly large. Font size of 100. Color will be a light gray. Apply our draft stamp, and then we will adjust the angle. Let's experiment with an angle of 45 degrees. Then adjust the placement of the draft text. Let's review and make sure our map contains at least the majority of the basic map components. We will revisit Last Dog. Legend, author, scale bar, title, date, orientation, grid. I think we're good. Let's print our map and get a copy to Michael. I'm not sure if I told you about this, but we are in the process of creating a new extension for ArcMap that will print directly to stone. Let's take a look at the beta version. Again, it's still in its infancy. After clicking this button, from this dialog box, we can pick and choose the type of dried fruit or berries we want to use for colors, including raspberries, gooseberries, and others. Our map has some red in it, so we could certainly use the dried or fresh raspberries and maybe some cow dung. Then our map, such as the one we just created, gets printed directly to stone. I can only imagine if the early Stone Age people had access to this application. On second thought, the stone is rather heavy, and it certainly would cost quite a bit to ship. Instead, let's create a graphic that we can email to Michael. From the main menu, choose File, Export Map. Let's set the Save As type to an Adobe PDF file. Keep the resolution at 300 dots per inch. Enter an output name and a destination folder. After the file has been created, we can open it or email it to Michael at the Breeze Power Company. You may recall we added yet another grid to our map titled Wind Power. This grid differs from the wind speed grid and may be more appropriate for a company with hopes of siting locations for power generation facilities. As a challenge, see if you can produce a map reflecting the wind power potential. And if you wish, email it to me at jfolgert@gmail.com. When creating a map, we can either create a map manually, like we just did, or we can use an existing map template. What is a map template? A map document, a map with a .mxd extension, is considered a map template. So believe it or not, the map we just created is a template, and we can create new maps from this template. Although a template doesn't have to contain base maps or layers, it often contains the containers, which will eventually hold the base maps or layers. Why use a template? Well, a template is a great place to begin when designing a brand new map. In addition, map templates can be reused. If we're creating a brand new map, we may wish to begin by selecting a template from within the Getting Started dialog box. This is the initial dialog box that appears when we open ArcMap. Note the two primary panels. The window on the left provides access to Map Template. We can select a map template that would match our project. Shortly after we began the creation of our wind map, we saved a version as version 1 or V1. Do you remember that? I think I do. Let's load that map document. Then we'll toggle to the layout view. Our goal is to use an existing map template to help us in the design of our map. We begin by choosing a new map template. From the layout toolbar, we'll click on this button called Change Layout. From the Select Template dialog box, numerous tabs are displayed near the top of the window. Click on the small arrows to the right to view additional tabs. After clicking the tab titled USA, the panel on the left provides the name of the template. After selecting a template, a preview appears in the right panel. Let's choose the second template and then click Next. We are asked to order our data frames to match the number shown on the new layout. The template does not have a vicinity map, though we will need to change the order of these items. We'll select the vicinity map and choose Move Down, and then click Finish. This becomes our working template, and within a very short period of time, we've organized the elements of our map. As another option, click Change Layout, click World, choose Asia, click Next, adjust the frame order, and then click Finish. Rotating a data frame can be an effective way of optimizing the full extent and shape of a standard rectangular piece of paper. The shape of Pend Oreille County lends itself pretty well to placement on a landscape piece of paper. In a case or example where a county is somewhat diagonal, such as what is shown in this example, the county is somewhat diagonal. And in order for it to occupy a standard page size, it is necessary to use a smaller map scale. Using a smaller map scale very well could reduce the amount of detail we can show on our map. By rotating the data frame, we can orientate the county so that it aligns with our rectangular piece of paper, and therefore we can show the area of interest at a larger scale and, quite possibly, show more detail on our map. I know what you're thinking.
If we rotate the data frame, north will no longer be up.
The good news is that when we rotate a data frame, the north arrow is automatically rotated as well. When rotating a data frame, we have a number of configuration options. We can manually enter the rotation value, for example, -40, or we can rotate interactively with the mouse. This map document includes a series of geographic information assets, including counties, lakes, and national forest. If we focus our attention on Mineral County, we observe that the orientation of this county is somewhat diagonal. If we toggle from Data View to Layout View, we notice that our current page setup is Portrait. We most certainly can fit the county into the standard page size, though we are not optimizing the full page. After toggling from Layout View back to the Data View, we can establish a rotation of our data frame so that Mineral County is drawn more in a vertical orientation. To set the rotation, we invoke the Data Frame Properties dialog box by double-clicking on our data frame. I will enter a rotation value of -40 degrees. Click Apply and then OK. If we zoom out to the full extent, we see that the entire data frame has been rotated. I'll go back to the previous extent and then toggle to the Layout View. In this example, we're able to generate a larger scale map after rotating the data frame. The county more fully occupies the full extent of our page. We observe that the north arrow rotated as well. A more interactive method of rotating a data frame is to first activate the data frame toolbar. Either right-click in this blank space and turn on the data frame tools, or from the main menu choose Customize Toolbars and select Data Frame Tools. Currently, the rotation is specified, -40. To clear rotation, we click on this icon with a red X in it. The rotation angle is then reset. To rotate a data frame interactively with the mouse, click on this tool called Rotate Data Frame, place the cursor on the data frame, press and hold the left mouse button down. As we rotate the data frame, the degrees of rotation will be displayed in the small yellow box. When the desired rotation is achieved, release the left mouse button. Thank you for being a part of this tutorial. The purpose of this tutorial was to provide an introduction to cartography and making maps with ArcMap.